Hi everyone. Today we're going to study recursively defined functions. What is recursive definition? Let us define recursion. It says the process of defining an object in terms of smaller versions of itself is called recursion. A recursive definition has two parts. Number one is the base. Second part is recursion. The base is an initial simple definition which cannot be expressed in terms of smaller versions of itself. The recursion is the part of definition which can be expressed in terms of smaller versions of itself. For example, this is now the definition for odd positive integers. It may be given as the base is 1 is an odd positive integer. For recursion, if k is an odd positive integer, then k plus 2 is an odd positive integer. Now, 1 is an odd positive integer by the definition base. For the recursion, with k equals 1, we have 1 plus 2 equals 3. So 3 is an odd positive integer. It follows that with k equals 3, we have 3 plus 2 equals 5. So 5 is an odd positive integer. And so 7, 9, 11, and so on are odd positive integers. Now let's go to recursively defined functions. A function is said to be recursively defined if the function refers to itself such that, number one, there are certain arguments called base values for which the function does not refer to itself. Number two, each time the function does refer to itself, the argument of the function must be closer to a base value. Example 1. Suppose that f is defined recursively by f of 0 equals 3. F of n plus 1 equals 2 times f of n plus 3. Find f of 1, f of 2, f of 3, and f of 4. Let's begin with f of 1. Looking at our f of n plus 1, we can rewrite this f of 1 as f of 0 plus 1. In here, n equals 0. Considering now the right-hand value of this function, we write here 2 times f of 0 plus 3. Let us substitute the value of f of 0 based on the given as value 3. So we have now 2 times 3, then plus 3. The product here is 6, then plus 3, we have 9. This is the value of f of 1. Then f of 2. Considering our f of n plus 1, we rewrite the f of 2 as f of 1 plus 1, meaning the n value is 1. Considering now the right-hand side value, we write in here 2 times f of 1 plus 3. The value of f of 1 we derive as 9. We substitute it here. So we have now 2 times 9, then plus 3. The product is 18, then plus 3, so the sum is 21. This is the value of f of 2. Then f of 3. Based on our f of n plus 1, we rewrite this f of 3 as f of 2 plus 1, which means the value of n is 2. With our right-hand value, we write here 2 times f of 2, then plus 3. Let us now substitute the value of f of 2, and that value is 21. So we have now 2 times 21, then plus 3. The product here is 42, then plus 3 is equal to 45. This is the value of f of 3. Then we have f of 4. Considering again this f of n plus 1, we rewrite f of 4 as f of 3 plus 1, meaning the value of n is 3. Considering the right-hand value here, we write here 2 times f of 3, then plus 3. The value of f of 3 we derived as 45. So we substitute the value here. So we have 2 times 45, then plus 3. The product here is 90, then plus 3, we have 93. This is the value of f of 4. Example 2. Find f of 2, f of 3, and f of 4 if f is defined recursively by f of 0 equals negative 1, f of 1 equals 2, and for n equals 2, 3, 4, and so on by the function f of n plus 1 equals f of n plus 3 times f of n minus 1. Let's begin with f of 2. Considering our f of n plus 1 here, we can rewrite f of 2 as f of 1 plus 1. We can see that the value of n here is 1. Considering the right-hand side value of this function, we write in here f of 1 plus 3 times f of 1 minus 1. This 1 minus 1 is simply 0. Now let us substitute the corresponding values for f of 1 and f of 0 as given here. F of 1 is 2 and f of 0 is negative 1. So we have 2 plus the product 3 and negative 1 here. So 3 times negative 1 is negative 3 plus 2, we have negative 1. This is the value of f of 2. Let's proceed with f of 3. Let us consider again this f of n plus 1, which means we can rewrite f of 3 as f of 2 plus 1, which means the value of n is 2. Based on the right-hand side here, we can rewrite this as f of 2 plus 3 times f of 2 minus 1. This 2 minus 1 is 1. Let us now substitute the corresponding values for f of 2 and f of 1 respectively. F of 2 is negative 1 and f of 1 is 2. So we have here negative 1 plus 3 times 2. 3 times 2 is 6. Then plus the negative 1, we have positive 5. This is the value of f of 3. Let's proceed with f of 4. Considering our f of n plus 1, we rewrite f of 4 as f of 3 plus 1, which means the value of n is 3. Let us rewrite this value based on this right-hand side. We have now f of 3 plus 3 times f of 3 minus 1. This 3 minus 1 is simply 2. Let us now substitute the corresponding values for f of 3 and f of 2, which are 5 and negative 1 respectively. So we have here 5 plus 3 times negative 1. The product of 3 and negative 1 is negative 3 plus positive 5. The answer is 2. This is the value of above 4.